start the recording. Is it? Has it started? I think. Okay, so today we're supposed to be talking. No, now it's started. Okay, fine. Today we're supposed to be talking about big O notation, which again is a topic we have covered, but it's not in the README file. So we just wanted to go over it again, just to make sure that we have it as a recording that anyone can go and then listen to. So yeah, let me just maybe share my screen and yeah, does anyone want to have a crack or try and explain what big O notation is? Anyone? Okay. Okay. So before talking, let me just share. Let's multiple share. Okay. Before talking about what it is and I wanna talk about why are we using it in the first place? Like, what's the point of big O notation? And from what I found out, the point is that we just wanna see how efficient a specific algorithm is. So, for example, let's say that you have a sorting algorithm, like you want to sort a bunch of numbers together. What is the best way to do this? So we could basically have just like a program and then run it, and then it would say, okay, this program ran in I don't know, a number of milliseconds. Like this one took 23 milliseconds. This one took 100 milliseconds. So the first one is better. But the problem with that is that it really depends on what language you're using. So for example, C++ is a lot faster than, say, Ruby. And it depends on the machine that you're running. So it's like a very subjective kind of way, and uh, it's not very accurate. It can change. It's not fixed. It's not really useful to be able to compare it with people that have different devices and people that are learning different languages. So instead, we'll use something called three things really. It's something called we've got Big O. Let me just I had it open. Yeah. So we've got something called Big O notation, which takes the worst case scenario. So you've got an algorithm assume the worst case scenario happens. How much time does it take, or how much time does it take to function? We've got something called the theta notation, I think. No, this is omega. Yeah, omega notation, which is best case scenario. Which is not really used a lot. I think this is not very useful. And then there's something called theta notation, which kind of takes takes the average of these two. And you might think this is like the one that we would use theta notation, but no, like we're not usually more interested in big O notation because we're not interested in the average. We're just interested worst case scenario, how long is my algorithm gonna take? So how is it measured basically? Like how do we go about measuring the thing with this? Yeah. So the idea is that anything that runs at constant time. So for example, let's say we've got I don't know, print hello world, and this is gonna take just it's called O1, I believe, or constant time. So this is just gonna take like this, is it? It's just basically constant time. It's just gonna take. It doesn't depend on the input. It doesn't depend on anything. It's just gonna run the same amount of time, no matter how many times I run it, or no matter how. Okay, let's make a function. Let's say define my function, and this function is gonna take an array, and then we're gonna end this. So let's see, Control X, Control V. So if I call my function, right? If later on I call my function and I pass in an array of say 3, 4, 5, 6, something, I don't know, something else. Yeah, That's not right. Okay. So if I pass in this function, or I pass in just like maybe one number, it doesn't matter. Like the function doesn't care. It's just it's not dependent on the input value. So this is gonna be one of them. Does the integrated terminal give you how much like the speed of things? So if I say LB index.lb, does it tell you how fast it was? I don't think so. No, it doesn't tell you about in the console. It doesn't matter. So we call this O one of time. So if I had this and I had it for like 100 different lines, this would still be called constant time or O of one, because it's not, again, it's not dependent on the, it's not dependent on the array. So the array can go as much as it wants, and this one to be affected. And of course, this doesn't have to be a print. It could be anything that you want. We could like maybe say assign a variable. So let's say my variable is equal to say 20, and then here we can say like have operations plus plus. It doesn't matter as long as it's plus equals 10, and you can have as many operations as you want as long as there's no loop in this thing. It's called an O1. Yeah, that's the idea of it. So what if it is dependent? Well, if it is dependent and we're looping through each element, say all dot each, and then do, and then we can say something like item, and then here, and then we say maybe print, and then my my item is, and here we could say something like item, right? Now this depends on this depends. What did I print? Yes, no, print. Okay. Now this is gonna. Okay, I don't want print actually. I want put so that I can see it. Clear. Yeah. So my item is 3. My item is 4, and to the end. So if I make this array like a lot bigger, this is gonna like it's. It depends on the size of the array. So if my array was say empty, it's not gonna take any. It's gonna take a lot less than if I had a lot of elements in it, because it depends on the size of the array, and this is called big O of n, right? Because it's gonna loop through each and every item. Say I'm gonna loop through the items until I find, for example, I could say return, or maybe break. I think break. Yeah. If say example is equal to say 534. So without this is considered a big O notation, because of course we're looping through each and every item. But what if I add this? So now it's gonna run undefined local variable method n. What? What line? 14. What did I do wrong here? My function n for main object. What? Do you guys see an n maybe? Okay, it doesn't matter. Let's just my function. Let's just remove this stuff for now.
Line 5.
Line 5.
Remove the O of n.
Oh, of course. Sorry. Control Z. Yeah. My bad. Okay, so now this is gonna. Yeah, it's only running up until 534. So what's the notation of this? Like you might think this is something short, but this is actually it's gonna be like big O of n, because again, big O is the worst case scenario. So in our worst case, we might not even have the item in this array, or it could be the last one. So in the worst case, it's gonna loop through all of the items in order to find it. So this is considered a big O notation, big O of n. Okay, so what about let's say, what about if we have an array and let's see, what can we do? Like, what if we had something like, okay, this is not very like a good example, but what if we had like an array of arrays or something? Um, mm, is that a good example? I don't know. Like, say for example, you had a class of people, and you were outputting, I don't know, maybe their grades or their favorite number or something, right? So, so this array would be something like, let's call it classes, okay? And each class would be like an array of favorite number, like class favorite or something, I don't know, like classes, this is just class. And then inside of each class, so let's say that each, I give very bad examples, I know, I'm sorry. Favorite number or something. And okay, so again, this is like we've got like a class or a group of people or anything, whatever this is, and then inside we've got like an array of the favorite number of each person. So I wanna loop through them, and I wanna output each and every I wanna output each and every yeah, like each and every number. So it doesn't matter, it's just a favorite number or something, right? And then if I output this, it's gonna be like a what did I do wrong this time? Classes dot each, okay. Oh, I think okay, maybe I can't use class, maybe class favorite something. Nope, still a mistake. Unexpected end. Do end again this thing maybe. Clear. Yeah, so it outputs each and every single number from each and every class. But in this case, the operation that we have is gonna be n squared, because we've got a for loop, and inside of that we've got another, like we've got a loop, and inside of that we've got another loop. So it's gonna loop. Okay, this is not a good example. What better example can you guys think of for like a loop inside of a loop? Let's see.
Like you're running a loop, like you're trying to compare two arrays together.
Okay.
Like say two separate left array, right array, and you say left array dot each do, then you run the left array against the right array, like run a loop inside another loop, then do some
Yeah,
logic
that
inside.
would be like a better idea. So let's see. Yeah, and then we've got maybe another. Okay. So let's give it a better example than this one. Okay, so let's say we've got two arrays, okay, and we want to compare them, and we want to see if they're the same thing, if they're equal. First array, and second. A bad way approach to this, or like a naive approach to this, would be to compare each and every number, and if they're not the same, I'm just gonna output that they're not the same. So I could say so. Or better, no. This is because it's gonna compare each one to another one. We could write, for example, a searching algorithm that would find one element in another array. Yeah, let's do something like that. So we've got one. Okay, so find if element in first array exists in second array. Okay, So what can we do? We could say first array dot each element in first array exists in second array. This is for each and every one of them, right? So yeah, we could do something like this. For example, all exists, and this is gonna be like a Boolean value, and we're gonna set it to true, and then we could say do item one, okay, and then second array each do item two, okay, and then to end. Okay, and we could say something simple like if item one return false, if I don't know, item one is not equal to item two. Right, so we're looping what? No, what am I saying? What am I saying? Find if element in first array exists in second array. Okay, so we want to loop through the second array. We're saying if item one is equal to item two, so item exists, something exists is equal to false. Okay, we could say if item one is equal to item two, then item exists is equal to, can I do this in Ruby? I'm not sure. Let's just do this to be safe. And okay, so if item one is equal to item two, we know that this item exists, and that's fine. And we could say, yeah, so we finished the second loop, and after finishing the second loop, we have visited each and every item. And then we could say if item exists, then we could say just go to the next one. Can I say else? Return false. I'm making this way more complex than it should be. Is equal to false, and then that's it. So first array dot each, and then I could just say return all exists, something like that. Let's check it out. Void value expression. Of course, it's fine. Why would it work? Why would it just work? It doesn't make sense. And yeah. Else. Am I writing it correctly, like as a syntax? I'm not sure. I think there's like a better way to do this, but like, never mind.
Line 12, sorry, line 12 and line the do there, I don't think that you want to return line 13, right?
I just want to tell, like, if the item exists, basically means that like the first item, I found it in the second one. I just want to go to the next item, right? Like I'm finished with the second loop. Now I'm in the, on the first loop, I'm saying if the item does exist, just go to the next item. If it doesn't exist, then give me, I mean, I could just do this. Like, why am I complicating stuff for myself? If item doesn't exist, then all exist is equal to false, and that's it. Like, why am I complicating stuff so much? Just this. This is fine. It's not fine, is it? Let's see. Let's see. Okay. Syntax at line 26. What's the problem with this one? Unexpected end of input, expecting end. So maybe if do and Okay, this has an end. This has an end, I think.
Have two do's.
Okay, it's saying like I'm missing an end, but I'm not sure where.
Yeah, where you have the second do in the first loop or
First
the
loop.
first if. Yeah, if you know after you have
At what line?
1, 2, 3. Yeah, 3 do's and 1 if. So you should have like I think 3 end.
So this one has an end. The second one has an end, and this one has an end.
Yeah,
Like
no,
at
what
what
he
line?
means, I
What am
think
I missing?
you're missing one more end after 14, I think.
After
Yeah,
line 14. Here, I should add
two.
like one more end.
Yeah.
Yeah,
Okay. I mean, I think I have it already. No, that wasn't it. Like, doesn't make sense. Two ends after one another. Like, this one goes here, right? This one goes here, this one goes here, this one goes here, and that one goes there. What's the problem then? Unexpected end of the input.
Try one more end at the end.
At the very end, just like put an
Yeah.
end there for a good measure. And yeah, no, just like put an end everywhere until it works.
No, because I thought maybe you weren't closing the official initial def.
No. Do, okay, we're inside of a loop, so we need an end, one end. We're inside of another loop, so we need another one. Third loop, okay, we close the third one, we close the second one, we open another one, close the second, or close the first one. You know what, we max
Try an end before the return.
What?
End before return.
What do you mean? I'm missing an end here?
Yeah, I don't know, try, maybe. I don't think so, but
Maybe it's not an end. Maybe the issue is not an end thing. Like I can't see well exactly on.
they do on line 12.
On line 12, what about it? Like, let me just.
Yeah, like you're saying if item 1 equals item 2.
Yes.
Instead of do, why not just say return this if this
Yeah,
is
I could do that. Like if you want, like return true if item 1 is equal to item 2, like this, which is the same as the one. I don't think that's the issue though. Nope. Okay. So this is a little bit clearer. Okay, we've got this, and this is the end. Okay, let's just copy this and like do the same. This is taking way too much time. Why is it taking so much time? It shouldn't. False. Just so that we can Control X and just put it here. Okay, so now I don't think it's maybe an end statement at all. Like, okay, so now it's working for some reason. Yeah. So let's just print out the result of this, which is gonna be true because now it's comparing each and every item to that one. Let's change one of them. Let's say maybe I don't know, like a very weird long. No, this is not even an integer anymore, is it? Just like that, which I'm pretty sure it's not in the first one, and it's still gonna tell you true. Well, this is a lie. Oh yeah, because okay, sorry. Let's just take this, Control C. And no, actually Control Z and put it here because it's checking the first one against the second one, not the vice versa. So this is still gonna be true for some reason. Why is this true? Doesn't matter, the algorithm that I wrote is not working. The idea is that it's basically a loop inside of another loop. So the idea of this algorithm, if it worked fine, would be to compare the first string, like each and every element in the second string, and make sure that it is in the second one. It's not working. I'm not sure why. I guess return false if item doesn't exist. Yeah, but it's not working. Yeah. So this is an n squared operation. Let's just keep it brief for now. N squared operation. Okay. So this is like the chart of the stuff that we could have. Like the O of n is like O of 1 is the best one. It's constant time. A meeting will end in 10 minutes, no problem. O of 1 is like constant time. It doesn't matter how large the input is. It's gonna run at the same time. Log of n is a bit better. So, for example, let's say what would be an example of log of n? It's I think a binary search is a log of n operation, right? Binary search time complexity. I think it's yeah, O log of n. So why is it log of, what does it mean log of n? It's basically something that it's not gonna search through the whole array or the whole input. It's gonna keep taking that input and making it smaller and smaller and smaller until it does what it needs to do. So, for example, let's say that we've got an array, but a sorted one. This is not sorted, but like if we had a sorted array, for example, let's just 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and 10. So a sorted array, let's say we wanted to find the number 6. So because this is sorted, well, instead of searching all of this, what the array is gonna do is gonna go to the middle one. So it's gonna go to maybe let's say instead of 5 we want 8. It's gonna go to 5, okay, and it's gonna say, okay, is 8 greater than or smaller than 5? 8 is greater than 5. So what it's gonna do, it's gonna remove all of these. So it's not gonna search 1, 2, 3, and 4. It's gonna remove all of that. It's gonna say, okay, I don't want to search that. Give me the second part of the array. And then it's gonna go to the middle of this one and say, let's say 7. I don't know why am I so lucky. It's gonna say, okay, I want the number that I want is 7. Can you guys hear me fine? I've got like a bit of a background noise.
Yeah, no problem.
Yeah. So 7 is less than 8, so that means I want to go to the left side of this. So I'm not gonna even look at 9 and 10. I don't know what they are. I don't want to know because I know 7, my number, is smaller than the currently mid number. So it's gonna look at 7. And now it's gonna maybe look at 7 and say, okay, this is the number that I want. The idea is that I didn't have to go through all of these. I just had to maybe search through 3 of them. That's the idea of the log of n. N squared, as we've seen, it's like a loop inside of a loop. And this is, okay, this is like stuff that takes a lot more time. I'm not gonna go into that because I'm not sure what good examples of them would be. Does anybody like have a good example of these two? Like
maybe a recursion, but I'm not sure.
Recursion, it depends on the type of recursion, but it's basically, it's O of n, like a basic recursion, isn't it? Like if I was to output, say, print my function.
For example, a Fibonacci recursion.
Say, for example, I had like, I wanted to print out the numbers from, I just wanted to print out the numbers 10, 9, 8, 7 like this. I could say number. Okay, we don't have a lot of time. I could say something like print and then number, and then I could say again my function, and then number -1. Then I could say if number is equal to 0, and then return some. Does that work? Why do I keep, okay. If number is equal to 0. Okay, so it's gonna, see, this is of an operation, right? It's just looping through like 10 or the input or whatever you have, and it's so it also depends on like the input. However, the recursion, it doesn't take. We're talking about time complexity, which is how long is it gonna take. We also have like something called space complexity, which is basically what are the extra variables or the extra storage that I need in order to make a function work. Yeah, and this is like some of the most used data structures and queue. Sorting algorithms, very common sorting algorithms, and how much they take. Again, you got something called time complexity and something called space complexity. This is like it's similar to time complexity, but let's say that, for example, let's go back to an earlier example. In this function, I had to create a variable to hold this one, and for each item in the loop, I had to create something called, I didn't have to create, I did it, something like a variable called item exists. So here I'm using two different variables. So here the space complexity would be O of 1. Like I'm using two of them, but I'm only using two. It doesn't matter how big these two arrays are. I'm still only gonna need these two variables. But say that, for example, I wanted to like the item exists. I don't want it to be like, let's say, I want to store, for example, this if the item exists for each and every item, right? Because what's that? Compose my function. Yeah, I want to make sure like each and every item of these, if each and every one of them exists, then I wouldn't store them like this with just like one variable. I would have an array of items that tells me that if each and every item exists. In that case, it would be O of n space complexity. Yeah, and I guess that's it. That's like the main ideas in Big O, and this is like a very popular cheat sheet. Not sure. Yeah, doesn't want to go big now, but this is it. Yeah. So I'm not sure, like, do you guys want to make a second part to the meeting? Because we don't have enough members. We it's just 3 of us right now. What do you think?
Yeah, everybody left.
Yeah, I think
What was the other thing?
we were supposed to talk about linked list and like some of their implementations. But I guess like the guy that asked us about it last time that wanted he had a question with something called how tall is the tree here and show up. So I'm not sure that if we should go into that. But yeah, that's it. Like if no one has some questions or he wants to share some code, I think we can just leave it at that. Short meeting today. That's fine.
As you guys want. I mean, I'm not the best yet on linked list, but if there is nobody else, I don't know if it's going to.
You want to try and no, we've explained linked list. It was linked list implementation using queues and stacks that we wanted to go to.
Okay.
Yeah, like you want to try and maybe share the code or show us?
No. I don't have. The last one I have to redo it for
Okay.
sure.
Okay.
In algorithms, I'm super behind, man.
No problem. Yeah, so I guess that's it for this week. Again, a very short video, and I don't know, maybe next week we're gonna go back to graphs now that we've covered the stuff that we had in the first 2 meetings. Yeah, so I don't know, maybe leave it in the chat what you guys want to do for next week.
Okay, buddy. So thanks a lot, man, for your time.
See you. Take care, guys.
So see you, buddy.
Thanks,
Thank you.
Ayman and Sergio.
Take care, dude.
Thanks to you guys. Bye-bye.